Hi, this is Dr. Bay and here's Bugsy, and today we're going to introduce alcohol reactions. We'll delve into how to form alcohols by substitution and by addition across alkenes, so stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Alcohols are compounds that possess a hydroxyl group, or OH group, connected to an sp3 hybridized carbon atom that are characterized by IUPAC names ending in OL or OL. So many bioactive molecules contain hydroxyl groups. For example, cholesterol is a molecule that is important in the biosynthesis of various steroids and contains a hydroxyl group highlighted in blue. Another molecule is vitamin D3, which regulates our calcium levels, and it also contains a hydroxyl group shown in blue as well. An important motif in many molecules is called a phenol, which is a compound that contains an OH group directly connected to a phenyl ring. One example of a substituted phenol is capsaicin, which is the molecule responsible for the spiciness of chili peppers. Recall that the acidity of a compound can be qualitatively analyzed by looking at the stability of its conjugate base. The conjugate base of an alcohol is called an alkoxide ion, where there is a negative charge on the oxygen atom. There are two ways to deprotonate a hydroxyl group. One way is to use a strong base like sodium hydride or NaH, where the hydride or H- deprotonates the alcohol. The OH bond breaks to form a new lone pair on the O, creating a -1 formal charge on oxygen, which then produces the alkoxide ion and hydrogen gas, which bubbles outside of the solution. Another way is to use a metal like lithium, sodium, or potassium, which react with the alcohol to produce an alkoxide ion as well. Alcohols can be formed by a substitution reaction where a leaving group is replaced by a hydroxyl group as shown in this general scheme. In this example, we have the following propyl bromide reacting with NaOH and DMF. In order to decide what type of substitution reaction this is, we should list out the factors of what we currently know. First, let's determine the type of alkyl halide. Remember that the carbon atom that the leaving group is attached to, in this case bromine, is called the alpha carbon. The carbons that are directly connected to the alpha carbon are the beta carbons. Since the substrate only contains one beta carbon, that means that this is a primary alkyl halide. Now, if we look at the base/nucleophile, recall that we can rewrite NaOH into Na plus and OH minus. Since OH- has a clear negative charge on the oxygen atom, this means that this is a strong nucleophile. Sodium hydroxide is also considered to be a strong base. And the next factor is the type of solvent. DMF, or dimethylformamide, is a solvent that does not have any hydrogen bonds in it, which means that this is a polar aprotic solvent. Now let's combine these three factors and compare it to our chart. According to the top chart, NaOH falls under the category of a strong base and strong nucleophile. Now having that information, we can take a look at the bottom chart. With a strong/strong base/nucleophile with a primary alkyl halide, this tells us that this mechanism is SN2. Since SN2 is a concerted one-step mechanism, OH- attacks the alpha carbon at the same time that the leaving group leaves to form a new lone pair on bromine. This produces a primary alcohol and NABR. In the next example, we are reacting a tertiary alkyl bromide with water. Water is both a weak base and a weak nucleophile, and water also contains hydrogen bonds, making it a polar protic solvent. Now looking at the upper chart, water falls under the weak/weak category. And if we look at the bottom chart, with a weak/weak strength and a tertiary alkyl halide, this tells us that the mechanism is SN1/E1. Since we're only focusing on alcohol formation, let's only show the SN1 mechanism here. Remember that SN1 is a two-step mechanism where first the leaving group leaves to form a carbocation intermediate, then a lone pair from the oxygen atom of water attacks the carbocation to form the following intermediate. Then in the last step, Br- comes back to deprotonate the extra hydrogen atom in order to form the overall neutral tertiary alcohol product. But keep in mind that E1 also competes with this mechanism. Since the E1 product is a tri-substituted alkene, it is the major product of this reaction, while the SN1 product is the minor product. Besides substitution reactions, alcohols can also be formed by an addition reaction across alkenes. For these reactions, be mindful of any Markov-Nikod's or anti-Markov-Nikod's rules. Recall that Markov-Nikod's rule is that the hydrogen goes on the less substituted carbon atom of the alkene, while the carbocation goes onto the more substituted side due to carbocation stability. In an example of acid-catalyzed hydration, H3O+ is being added across the following disubstituted alkene. First, the pi bond of the alkene breaks and grabs one of the hydrogen atoms of H3O+. Since this reaction follows Markov-Nikod's rule, the hydrogen will go onto the right side or the less substituted side of the alkene, while the carbocation forms on the left side of the alkene. Then water attacks the carbocation, and another mole of water is used to deprotonate the extra hydrogen atom to form the alcohol product. Keep in mind that this reaction may have carbocation rearrangements if you can form a more stable carbocation. Two more addition reactions that can form alcohols are oxymercuration, demercuration, and hydroboration oxidation. Oxymercuration demercuration follows Markov-Nikod's rule, where the alcohol is added to the more substituted side of the alkene, and hydroboration oxidation follows anti-Markov-Nikod's rule, where the alcohol is added to the less substituted side of the alkene. So in summary, there are two reagents that you can use to deprotonate alcohols. You could use a strong base like NaH or a metal like sodium, lithium, or potassium to form an alkoxide ion, which then could be used as a strong nucleophile in a subsequent reaction. Alcohols could also be formed by a substitution reaction, and its mechanism will depend on the type of alkyl halide. And alcohols could also be formed by addition across alkenes. Both oxymercuration, demercuration, and acid-catalyzed hydration add an alcohol to the more substituted side of the alkene, while hydroboration oxidation adds an alcohol to the less substituted side of the alkene.
Organic.